Hi guys, I'm going to walk you through a little bit on the central limit theorem. So we're going to talk about chapter 7 in your packet. So if you go to page 395, I'm going to do the same. So as I switch this stuff around, getting your packet to page 395. There we go. All right, so now as we go through this, just know that I'm only going to do the first introduction and then section 7.1 as we go through on this. Okay, so on the next page it talks about the central limit theorem. We're going to use CLT for short. It's one of the most powerful ideas, and it allows us to, when we know the mean and the standard deviation and we have a large enough sample size, that when we create the histogram, the resulting histogram will be in a normal distribution or a normal bell curve. So this is probably the key right here. It's going to approximate the normal bell curve. And we just have to make sure we have a large enough sample size. And this works for both the means and the sums. And this part right here is probably the most important, that the distribution of sample means and the sums tend to follow a normal distribution. It can have a different underlying distribution, but that's the key, is that it will follow a normal distribution. And that your sample is large enough, so you need to have at least 30 in your data set for your sample, and or your sample size, and that your sampling is done with replacement, so that your sample is with replacement. All right, so now as we start into 7.1, a couple of things to note is that remember that this is a free textbook, so there are a couple typos. This is not mu times x, this is the mu sub x, and it's the same thing on the standard deviation. Right? So we're starting off with a random variable, and this can come from any distribution. So this could be binomial, this could be geometric, this could be exponential. The underlying distribution, I mean, it could be even uniform, we don't know. So on this one, for this to work, it can be coming from any kind of distribution. All right, so up here on the top, that's the other part of that typo. This should be the standard deviation, or sigma sub x, not times x, as it's typed here. All right. All right, if you draw random samples of size n, as n increases, the random variable x bar, so this is not just a sample, this is a sample of means. Okay, so that's why it's x bar. And this is called the sampling distribution of the mean. It tends to follow a normal distribution. So this is how we would write out that normal distribution. So here is our mean, and then to find the standard deviation, we divide by the square root of n. The central limit theorem says that we keep drawing larger and larger samples, that calculating their means, the sample means from their own normal distribution, and this is going to follow a normal distribution as we keep increasing n. And then we can calculate a z-score, but this is a different z-score. This one is associated with the mean rather than just the random variable x. So this is how you would calculate the z-score using the random variable x bar. And then if you can look at this, mu, the average is the same for both x and x bar, and then this standard deviation is a little bit different. So you have to divide by that square root of n, and the standard deviation for x bar, which is the standard deviation for the x divided by the square root of n, that's your standard error of the mean. Okay, so now we're going to kind of walk through how you would put this into a calculator. All right, so you're going to go to your distributions. You're going to do a normal CDF, okay, and the mean is the original, the mean of the original distribution. Your standard deviation is the standard deviation of the original distribution, and our sample size is n. Okay, the big difference on this is that your standard deviation for the mean has to be divided by the sample size. Okay, so your lower value of the area, upper value, your mean, and then your standard deviation divided by the square root of the sample size. All right, so now we're going to walk through example 7.1. This is on page 397 of the packet. So an unknown distribution has a mean of 90 and a standard deviation of 15. The sample size of n equals 25 are drawn randomly from the population. So this, once again, this is an issue of a free textbook. Right here, this should be at least 30, okay? So in order for this to be true, because remember our criteria, we need to have a large enough sample size, and 25 is not at least 30. So just chalk it up to a free textbook, but we'll still go through this as an example so you can see how to type this into your calculator. All right, so we're going to find the probability that the sample mean is between 85 and 92. So we're looking for the sample mean is going to land between 85 and 92. All right, so our random variable, we're looking at the mean of the sample size, and this really should be at least 30, but we're just going to roll with it as the 25. Okay, and our mean is 90, the standard deviation is 15, and n is 25. So using this, we're going to put it into a normal distribution, and this is how we're going to put it into your calculator. All right, so let's put this in. You need to go to your distribution, so that's using your second key, and we're going to do a normal CDF. Okay, we need our lower limit is going to be 85 because we're checking to see the probability this falls between 85 and 92. So the lower limit is 85. The upper limit is 92. The mean is 90, and the standard deviation, this is going to be 15 divided by the square root of 25. And we get 0.6997, okay? All right, so once again, we did a normal distribution, a CDF, our lower limit, our upper limit. We had our mean and our adjusted standard deviation for the n size of 25. And this is where we're finding the probability that it lands between 85 and 92. And we got 0.6997. All right, so now we're going to walk through example 7.2. This is on page 399 of your packet. And I'm not going to go over the try-its, but you should be doing those on your own. All right, so the length of time in hours it takes an over 40 group of people to play one soccer match is normally distributed with a mean of 2 hours and a standard deviation of 0.5 hours. A sample size of n equals 50 is drawn randomly from our population. Find the probability that the sample mean is in between 1.8 hours and 2.3 hours. All right, so we have a sample size of 50, and that is large enough. We also should have checked to see if this was done with replacement, but they don't give us enough information on that, but we're going to assume that this is done with replacement. All right, so as we walk through this, we know our mean is 2 hours, the standard deviation is 0.5 hours, and our sample size is 50. So we're trying to figure out the probability that the sample mean lies between 0.18 hours and 2.3 hours. All right, so we're going to put this into the calculator. Once again, you're going to go to your distributions. This is a normal CDF. Okay? And our lower limit is now 1.8 hours because we're looking to find the probability that it goes between 1.8 hours and 2.3. So the lower limit is 1.8. The upper limit is 2.3. And our mean is 2 hours, and then our standard deviation is 0.5, but this has to be divided by the square root of our sample size, which in this case is 50. All right, so then that gives us the probability that it lands between 1.8 hours and 2.3 hours is 0.9977. And if we're looking to find percentiles, we're going to do the same thing that we did before. We're going to use the inverse normal function and then use k as the percentile and use our mean and then our standard deviation divided by the square root of the sample. All right, so now we're going to go through example 7.3. This is on page 400 of your packet, 7.3. In a recent study reported October 29th of 2012 on the Flurry blog, the mean age of a tablet users was 34 years. Suppose the standard deviation is 15 years and take a sample size of n equals 100. There are 4 parts to this. Part A, what are the mean and standard deviations for the sample mean age of tablet users? Then B, what does the distribution look like? and C, find the probability that the sample mean age is more than 30 years. Okay. Then we're going to look and find the 95th percentile for the mean, or for the sample mean of age. All right, so the mean is going to be the same. So if our mean was 34, it is still 34. And the sample standard deviation is going to be the standard deviation divided by the square root of n. So this is going to be 15 divided by the square root of 100, which is 1.5. Okay, part B was asking, what does the distribution look like? Well, this is going to be normal distribution. Okay, so it's going to follow that bell curve. Okay, so it's going to follow an approximate normal curve. So this is where we're using the central limit theorem to state that this distribution can be approximated by using the normal distribution. Remember that the underlying distribution, it doesn't matter what kind it is, that if we're talking about the means, it will approximate a normal distribution. All right, let's talk about part C. So we're finding the probability that the mean age is more than 30 years. So 30 is going to be our lower limit, and then we're going to do a really large number for our upper limit. Okay, so we're going to go to our distribution, and this is a normal CDF. So instead of going to the left of 30, we're going to go more than 30. So our lower value is 30. Our upper value is going to be 1e to the 99th. So that's 1 and then e to the 99th. That's going to give us our large number on the top. Our mean value on this one is 34 years. And then our standard deviation, so we have to do that 15, but then we have to divide it by the square root of the sample size, which in this case is 100. So you can type this directly in like this, or you could use the 1.5 we did earlier. Okay, so you can put it in either way. All right, so now we paste that in there. Oh, got an issue. Okay, I was just missing one of my parentheses, so maybe it's easier to put in the 1.5, but I went back and fixed that, and so now we have the probability is going to be 0.9962. Okay, so 0.9962. All right, so now we're going to do the 95th percentile. So we're going to go to our distributions and then do the inverse so that we can find our percentile. So we're going to do the 95th percentile, so we enter that in as 0.95. And then our mean is 34. And our standard deviation is the 15 divided by the square root of 100. So I don't want to make the same mistake I did last time, so I'm only going to put in the 1.5. And we get that the 95th percentile is 36.47. Okay. All right, I think that sets it up for the central limit theorem and talking about how it works with means. So I hope that helps you, and remember that we're going to have class sessions on Wednesday during our normal scheduled time, and then also you can schedule one-on-one help on Fridays. Hope you guys are doing well. We'll see ya.